Good night, Professor. This group is formed by Oscar and me, José Regalado. In this seminar, we have prepared a presentation related to the Lorenz system. So in order to begin, let's get started with the introduction. So it's continue my classmate, Oscar.
Hello, my name is Oscar. Um, my topic is the Lorenz system. The first question is, what is the chaos? What is the chaos? The chaos refers to a state of complete disorder and unpredictability, often arising in complex systems where small changes can lead to vastly different outcomes. It challenges our understanding of causality, suggesting that even in system government by deterministic rules, the result can be highly unpredictable. The concept of the chaos is deeply connected to the history of the Lorenz system, which were first introduced by meteorologist Edward Lorenz in the 1960s, in the 1960s, in the years 1960. While studying weather patterns, Lorenz discovered that a small difference in initial conditions could lead to vastly different outcomes in weather simulation, and phenomenon now is as the butterfly effect. This sensitivity, this sensitivity to initial condition is hallmark of chaotic system. Lorentz work demonstrated that deterministic system, like weather models, could exhibit unpredictable and seemingly random behavior, fundamentally challenging the traditional view that such systems were always predictable if enough information was known. His finding laid the foundation for chaos theory, revealing that even simple system could lead to complex, chaotic behavior. The lower system is a set of the three couplet nonlinear differential equations that describe the motion of the fluid convection in the atmosphere. The system is represented by the following equation. This equation, we denote the system if x prime equal to L depend x. In the system, x represents the rate of conductive flow, y the temperature difference between ascending and descending current, and c depend depend and c the deviation of the vertical temperature profile from linearity. The parameters sigma, rho, and beta are constant. Sigma is the Prandtl number, rho is a Rayleigh number, and beta is the geometric factor related to the physical dimension of the system. This equation together capture the essence of the chaotic behavior, where a small change in the initial condition can lead to wildly different outcomes, and hallmark of what is now as a chaos theory. A continuation is the simulation of GeoGebra. In GeoGebra. This is the simulation, the definition of the equation and the constant and the initial condition. Continuous is solution of system equation of numerical of method numerical is the graph, the simulation of the system, of the Lorenz system. All right. Continue. Yeah. It's important the study of the equilibrium point of the system of the differential system equation. The equilibrium point of the Lorenz system is as usually to analyze the system. We begin finding the equilibrium. Some easy algebra yields three equilibrium points: the origin and this expression. The last two equilibria only exist when R is greater to 1. So already we see that we have a bifurcation when R equal to 1. Linearizing, we find the system this expression. At origin, the eigenvalue of the matrix are minus b and this 2 lambda. 2 lambda. Note that both lambda are negative when are between in 0 and 1. Thus, the origin is as seen in the case. The Lorentz vector file L depend X possess a symmetry. If we let the function f, then we have differential s in L of x equal to L depend s in x. That this reflection through the z-axis preserve the vector field. In the particular, if xt, yt, and ct is a solution, c of t, this component depend of t, then so is minus x of t minus y of t c of t. All right, and when x and y equal to 0, we have the derivative is equal 0. So z-axis is invariant. On this axis, we have simply 6 prime equal to minus b c. So all solutions tend to the origin of the axis. All right, it's important three results, three propositions. Is the one proposition is suppose R less than 1, then all solutions of Lorenz system tend to equilibrium point of the origin. We construct a strict Lyapunov function of all on all of R3. Let L depend x, y, z equal to this expression. No? This function is a strict Lyapunov function since for the region is equal 0. And this function is positive uh, if different points of the equilibrium point at the derivative is this expression. This expression, since this expression is negative, then the strict function Lyapunov function, the derivative is negative for all different points of the equilibrium point and are less than 1. How the strict Lyapunov function is defined in all R3. Then all solutions tend to equilibrium point at the origin. All right, the proposition 2 is the equilibrium points are since provide R are between 1 and R and this expression. This solution is important of the graph, this characteristic polynomial. This is function is the value R. To rod, one rod. This is important of the proof of the proposition. All right, the proposition 3, there is there exists there exists eta star so that any solution that starts upside the ellipsoid v equal to eta star eventually enter this ellipsoid and the remains trapped there in for all future time. All right. The Lorentz attractor. The behavior of the Lorenz system of the parameter R increase in subject of the much contemporary research. We are decades, if not century, away from right or careful understanding all of the fascinating dynamical phenomena that occur after the parameter change. In the section, we will deal with a specific set of the parameter where the Lorenz system has an attractor. Roughly speaking, an attractor for the flow is an invariant set that attract a nervy solution. The following definition is more precise. Definition: let X prime equal to f depend x. Be a system of the differential equation in Rn with flow flow if phi sub t. As said, lambda is called an attractor if 3 point. The 1 point is lambda is a compact and invariant. There is an open set U containing lambda such that for each x in U, phi sub t depend x in U and intersection al closure phi sub t in U equal to lambda. The tree definition is transitivity. Giving any points y1, y2 in lambda, and any point neighborhood U view about y in U. There is a solution curve begin in mu1 and letter spaces through mu2. All right, it continues. My partner is Josué Regalado.
All right. Now, I will be starting by explaining why the Lorenz attractor is. It's a key concept in chaos theory. Well, this attractor was discovered by Edward Lorenz, as my partner said before, in the 60s, while working on a simplified model of atmospheric convection. Well, the Lorenz attractor is a set of chaotic solutions to the Lorenz systems. Although the Lorenz system is deterministic, it exhibits chaotic behavior. Now, what does it mean? It means that it exhibits chaotic behavior. The system follows precise laws but extremely sensitive to initial conditions. As a result of that, two trajectories that start very close can quickly diverge, leading to the very different behaviors. Now, what are our goal in this presentation? Is to understand, go back, please. Okay, is to understand how the Lorenz attractor can be modeled geometrically based on the work of Guggenheimer and Williams. We'll explore how a simplified model can capture the essence of this chaotic behavior. Now, continue, please. Now, let's talk about the symmetry. The model assumes that we are studying the system under a reflection, meaning that we have a point with coordinates x, y, and z that is showing we are showing here, that goes to the reflection with the first component as minus x, the second component minus y, and the third is invariant. Okay, this property is very important because it reflects the inherent symmetry of the original Lorenz system. Now, about the equilibrium points, okay, we place an equilibrium point at the origin, 0, 0, 0, in the three-dimensional space, R3 in other words. Why this is relevant? Because at this point, the forces in the system balance and there is no movement. However, the equilibrium is unstable, meaning that any small disturbance can cause the system to deviate. Continue to the, yeah, that's what I'm talking about. Now, let's define this cube S, defined by these three intervals bounded by 5. This is, we have three absolute values of each component of this point, x, y, and z. And we can say that this system behaves linearly. In other words, the system is linear. Now, this allows us to simplify the equation and focus on how small disturbances can lead to complex and chaotic behavior. Now, let's go with another slide. Continue, please. Now, we have the linear system in the cube S that we has just defined, okay? We analyze the linear system governing the behavior near to the origin. Now we have this equation defined like this, with the x prime, y prime, and z prime. Now, this equation describes how the coordinates x, y, and z change over time. Now, the agent continue, yeah, stop right there. The eigenvalues of the system are lambda equals -3, lambda 2 equal 2, and the last lambda eigenvalue is -1. Now, what are these implications? In the x direction, we can say there exists a strong contraction. It means that any displacement in x tends to shrink, to contract quickly. Now, as for y direction, there is an expansion, the contrary of the contracting, indicating that there is a small displacement in y grows over time. Now, last one with z direction, there's also a contraction, but it's weaker than x. We have a comparison between the z direction and y direction. It depends of how strong are those. Okay, this combination of expansion and contraction is what generates the complexity of the system, allowing nearby trajectories to separate and creating the chaos we observe in the Lorenz structure. Now, let's continue with another slide, please. Now, let's explore how solutions behave when they are near to the origin. Now, let's imagine the rectangle R1 that in the next slides, we are going to see how it's plotted in a graphic, okay? So we are going to describe it first, and then we are going to see it in a graphic, okay? Now, imagine the rectangle R1 in the plane C equal 1 defined by this interval that is the absolute value of x less than or equal 1, and theta between 0 and 1, including the number 1. Now, as the time progresses, the solution start in R1 moves toward another rectangle R2. Now, this new rectangle R2 is in the plane y equal 1. Continue by in the same slide. Now, this is where we have to define a mapping function, h, okay? This function tells us how coordinates in R2 transform into coordinates in R2. This is a mapping. We have this expression or corresponding rule. We have our mapping function here defined by h. Now, what's interesting here is how lines get disturbed under this mapping. Now, let's continue with the same slide. Yeah, stop right there, please. Now, what can we say about this mapping function? H maps lines in the plane y equals c in R1 to the lines in the theta c equal to c to the square of 1 over 2, or the square of c in R2. And the same in the plane x equal to c into the curve of the form to c c times of c sub 1 to the third. Now, let's continue to the next slide. Okay. Now, let's talk about the equilibrium points and the stable surfaces. Now, we also introduce additional equilibrium points in the plane c equal 27, and these points q minus and q plus. That's one of between them are reflections. Let's see that in the first and the second component, if we compare them, the first component only changes in the sign, where one of them are plus and the others are minus. Okay, these points are important because they represent additional stable states in the system. Okay, the lines y equals to plus minus 12, c that this is the plane 27 are portion of the stable lines at q plus minus of in other words, the combination of these points. Now, meaning, what does it mean about this description? This means that the trajectories approaching these points tend to remain on these lines. Continue in the same slide. Now, okay, let's talk about the unstable and stable surfaces. We have two details important to say here. Now, the stable surfaces at the origin intersects the square, and here we are going to define the square as this Greek letter as sigma, defined like this, that are a big rectangle of side of length 20 in the plane C equal to 27. In the next slide, we're going to see how is this square represent. Now, this square in the line intersection of the XC plane and the sigma. These are the superfaces of this origin meets in this square. Now, the unstable curves that we are going to denote like this with zeta plus minus make a passage around the sigma, or in other words, in this square, and enter to this square. Okay, these superfaces and curves plays a crucial role in how the system's trajectories evolve and eventually form the Lorenz attractor. Continue, please. Now, this is how we we understand the graphic of the rectangles R1, R2 that we described before. This is the behavior that this system has. Okay, this is how the solutions are behaving around the origin. Continue. Continuing the same. Okay. Now we are in the next step of this presentation is the return and mapping conditions. Now, what is the key of this? Is to understand how the trajectories return to the square sigma, okay, after leaving it. This is known as the return conditions, okay? Here we define another function, another map named Poincare map that is defined by the union of the sigma plus and sigma minus. Now, what is the meaning of these denotations? Well, in the context of the Lorenz system, sigma plus and sigma minus refer to regions of the square entirely. In particular, sigma plus represents the upper half of the square sigma, the superior part of the square. In the other side, sigma minus represents the lower half of sigma. In other words, specifically when the y is negative within the square, okay? Now, this union goes to sigma. We have the union of the positive and negative part of the square and goes to the entire square. Now, let's continue. Okay, no, don't go, don't. Return. Now, we define this mapping, and this might be fundamental to understand a structure of the tractor. Now, what we can say about this mapping? Three conditions. The contraction in X, the map phi contracts trajectories in the X direction, meaning differences in H are reduced, okay? And expansion in Y, we can say that phi stretches trajectories in Y direction by a factor greater than a square of 2, amplifying differences in Y. And the last one, hyperbolicity, the map that we are defining here that is based on the Poincare map satisfies this condition, that the first derivative of the second component of this map is greater than 2, and the partial derivative of respect to x is between 0 and a c that is less than 1. Okay, let's continue. Now, this is how the square sigma is placed in the xc plane. How is this square looks in this graphic? This is the sigma plus and the sigma minus are shown here. This is the positive part of the square and the negative part of the square. So this is important to understand how geometrically this Lorentz attractor works. Now, let's continue. And this is the Poincare map that we have just described. That is defined by this square and in these conditions, okay? We have an interval in the vertical axis that is the minus y star and the positive y star. Let's continue. Now, definition of the attractor. Okay, the attractor we define as the infinite intersection that begins in n equal to 0 of the closure of this Poincare map to the end in R, where R is the rectangle that satisfies this condition, that the y in the absolute value is less or equal to the y prime, that this element was shown in the graphic of the Poincare map. Always all of this inside the square that we defined before as sigma. Okay, continue in the same slide. Now, stop. Okay. The trajectories within the trajectory A, we define this attractor as the letter A, can have two possible behaviors. They may tend to the equilibrium point at the origin, okay? Or the other possible behavior, they may continually reintersect the rectangle R with distances between intersection points tending to 0. Now, this behavior is characteristic of chaos, where trajectories infinitely approach a set of points. Okay, that is how this attractor works. Let's continue. Now let's talk about the last topic of this presentation, that it refers to the chaotic attractor. Continue. Now let's talk about the reduction to one-dimensional map. If we recall how we defined the Poincare map, we define it in the third dimension, or the three-dimensional space, because it was a component of the square that was in the xc plane in the third dimension. But we're going to decrease one dimension, and we are going to work with the two dimension of the Poincare map. Now, we do this to simplify the analysis. We can reduce the system to one-dimensional map. Now, is only to focusing on the y coordinate. Now, the function, the new function to this dimension is defined as g of y. Continue. Continue. Okay. The function g that is presented here is defined in the interval minus y star to y star, satisfying these conditions, that the image of 0 is 0 and that the first derivative with respect to y is greater than square root of 2. Now, what is important here is how this function transform one y one y, or in other words, the the variable that this function has into another, and how this controls the system evolution. Okay, now let's continue with another slide. Now we are going to talk about the chaotic dynamics. Discuss the behavior of orbits under one-dimensional mapping. Now we have two kinds of orbit, the forward and the backward ones. So the forward orbits are the points generated by iterating the function g forward. That is, that we have this type of points, y sub 0, y sub 1, and etc., where each component is obtained by applying the function g to the previous value. This sequence describes how a trajectory evolves over time. Okay, now, uh, with respect to backward orbits, it's defined as this kind of point, where y sub 0, y sub minus 1, and etc. And we look backward in time to find out where a given point came from. This generates this kind of point, which each component is the preimage of the g sub minus k plus 1. Now, what's interesting is that the most points in y, there is a multiple possible trajectories that could lead to it, creating a vast number of possible backward orbits. Sorry. Now, continue. Now, about the structure of the tractor, we have seen that the tractor A intersects its line y equal to y sub 0 distinct from y star and infinitely many distinct points. This implies that within the tractor there is an infinite number of possible trajectories that infinite approach a particular line. However, these trajectories don't repeat in a simple way. They exhibit complex and chaotic behavior. Now, the last slide, I think, continue, please. We have the sensitivity and the pyrosity. Now, we have the sensitivity dependence on initial conditions. Okay. One of the most fascinating features of a chaotic system is its sensitive dependence of initial conditions. This means that if we start with two states that are extremely similar over time, their trajectories can diverge dramatically. This phenomenon is also known as the butterfly effects, that, as my partner Oscar said before at the beginning of the presentation, where the small initial differences can lead to vastly different outcomes. Now, regarding to periodic points, continue. Continue? Okay. A coded system like this has periodic points that are dense in the interval I, that is defined at minus y star to y star, okay? This means that any small neighborhood within the tractor, we can define at least one point whose trajectory is periodic. This existence of these periodic points combined with the transitivity and sensitivity is what makes the system chaotic. Now, about the implication for the flow, okay? For the flow, in the context of the overall flow in the system, these periodic points are like small islands of repetitive behavior within a sea of chaotic trajectories. But because these points are dense, almost any point in the trajectory is close to one of these periodic points. Now continue to the last slide, please. Okay, continue. Continue. This is it? Okay. It's okay, it's okay. Now let's talk about the transitivity and chaos. Okay. Any initial state can, in principle, evolve to approach any other state within the system. This means that the system is highly interconnected and there are no isolated islands of behavior. Everything is linked. Okay. Now we can say a summary of this chaotic behavior. We covered the three key properties that define the chaos in the Lorenz model: sensitivity, when the sensitive dependence of initial conditions, dense periodic points, and transitivity. Now, these properties, when present together, allow us to classify a system as chaotic. This is important because it tells us that even though we can understand the rules of the system and describe its dynamics, we cannot predict its long-term behavior precisely due to the inherent complexity of chaos. Now we are done with the presentation. Thank you so much.
Thank you so much.